As we conclude this chapter, we look at an example that highlights the similarities and differences between the two different methods we've looked at, the HPPC method based on a simple cell model and then the bisection method based on a complete cell model. This used real lab data, and here is a trace of state of charge versus time for the cell test that was performed, and you can see that there's a sequence of dynamic profiles. In this case, they were UDDS cycles that were biased to be a little bit to increase charge a little bit. So in one cycle, the SOC increased by about 5%, but then between each cycle, there's a discharge pulse that brings SOC down by about 10%. So the combination brings SOC down by about 5% per combination of UDDS plus the discharge pulse. The operating range of this cell was chosen to be between 90% and 10% state of charge. And this test exceeds both ends of that a little bit to see how well things perform inside and outside those ranges. The ESC model was fit to this particular cell, and we looked at the model behavior versus the true cell terminal voltage behavior in an open loop setting. The blue line in both of these plots is the measured voltage. The green line is the estimated voltage using the model. The left plot is for the whole test. The right plot is for one UDDS interval plus, you can see the discharge pulse and rest immediately preceding and following that UDDS profile. There's very good modeling, very little mismatch. The RMS estimation error in this case was less than 5 millivolts. For the test that we were doing, we were assuming a pack of the lithium-ion cells with 40 cells in series and one cell in parallel. The cells had a nominal capacity of 7.5 amp hours, and our prediction horizon was 10 seconds. And the table shows the operational limits that we were looking for. So a minimum voltage of 3, maximum 4.35 for this cell. The lowest current of minus 200 amperes, maximum of 200, minimum state of charge 10%, maximum 90%, and then there were no specific design limits on power itself. Used the HPPC method and the bisection method to produce power estimates, plotted in this graph on the right here. And in the discussion of these results, I'll consider the bisection method to be the true capability of the cell. Of course, there can be errors in that calculation, but we noted that the cell voltage predictions were so close for this cell model that it's actually going to be pretty good. And the HPPC uses a much simpler cell model, so its predictions are not likely to be as good. So while we don't know exactly what the true power capabilities are, the assumption that the bisection method is giving at least very, very close predictions of that, I think, is justified. So first, overall, the methods are not just completely different from each other. We see that both of them are producing estimates that are quite similar. Over here, you could say, wow, there's a big difference, but that's really only because when I ran the HPPC code there, I did not include SOC limits. I used voltage limits only, whereas the bisection method was including both SOC and voltage limits, and so it's kind of not comparing the same thing there. If I had included SOC limits on the HPPC method, we would have had very similar results there also. But we do see that high states of charge, the HPPC method overpredicts how much power is available. At lower states of charge, it seems to underpredict how much power is available, and by really quite a lot, by as much as almost 10%. In the middle range, we get quite similar predictions. The bisection method included state of charge bounds from a Kalman filter when I was doing this, which, it included SOC bounds on the power estimate. It also did use SOC bounds from the Kalman filter, but this here is explaining that phenomena that we talked about, was that there were limits placed on SOC, and that's why the bisection method results look quite different there. If we assume that the bisection method is right, then if the vehicle controller were to use the HPPC method limits, the cell would be over-discharged in some cases, which would lower its lifetime, or underutilized in other cases, which neither one of those we would like. This figure here is a zoom of the previous plot, showing more detail in the intermediate region, just to show that there are similarities, but there are differences between the methods. There's nearly identical predictions, but some of the characteristics are quite different. So the bisection method uses the full cell model, so it takes into account the entire dynamics of this cell. Something very interesting happens here. So HPPC is using SOC only, and I'm doing a big discharge right there, and then a rest. And during that time, the HPPC method is saying that I just have constantly changing power because of that. Whereas using the entire cell model, you can see that as I'm doing the strong discharge, it's really lowering the power capability because of it, because I'm biasing the resistor-capacitor circuit that models the diffusion voltages. But as soon as I stop discharging, the power that's available for discharge in the future rebounds quite a bit. So it's saying that that as that RC filter in the model is discharging itself, that there's this capacity for extra discharge power because of that. And it's quite it's noticeable here. Notice over here it's even more noticeable. I'm showing the case where the two are the most similar. So after I've just really accelerated, I don't have a lot extra for a few seconds, but then as I rest, as I coast, then it's kind of recharging, if you will, the ability to do a deep discharge again in the future. So I could do a deep discharge here, and the bisection method is telling us that, whereas the HPPC method is not really reflecting that at all. Looking at charge power, the methods are compared on this plot to the right, and this looks actually quite a bit more similar. The bisection method again does include SOC limits, so it's a little bit different, but there's some similarities throughout the entire range here. This is absolute power, by the way. I flipped the negative into a positive. If I look at a zoom, again we have this interesting thing here that when I've just done a deep discharge, the charge power capability of the bisection method goes up. It says if I've just really floored the accelerator pedal to pass a semi-truck, if I need to hit the brakes, to pull in front of the truck, I can do that, and it's telling me I can do that, whereas the HPPC method is not saying that I can do that because it's based on SOC only, not the full dynamics of this cell. So that could be a significant difference. In any case, we've looked at both methods and we've seen how they work. So we've looked at two methods to predict battery discharge and charge power, the HPPC method and the bisection method. Both incorporate voltage limits, state of charge limits, power limits, and current design constraints. Both work for some user-specified prediction horizon. The results that we saw indicate that the two methods produce actually quite similar predictions from each other. However, in a dynamic setting, the bisection method is going to produce much more dynamically changing results that are going to reflect, I think, quite a bit better what's really available in terms of power capability. The bisection method is harder, computationally more significant to implement. We saw some ways of minimizing that by pre-computing that summation. However, it does require quite a bit more effort to bisect at every point in time to get the power limit. But if we use a common filter to estimate state of charge, then the cell model already has the present state available for use as the input, as the initial state of the bisection, and I can use the error bounds on that state also as input to the method to produce conservative but tight bounds to the available power that's actually could be used. The bisection method is giving us these dynamic power estimates. It can take advantage of a recent strong discharge to increase the temporary available charge power and vice versa. So it can take advantage of strong charges. So if I had just jammed on the brakes, well, that means that I've got much more discharge power available right now too in the very near future. So the bisection method is a much more dynamic estimate of how much power is available, and I think much closer to the truth. So that brings us to the end of the chapter, and the assumption that we have made throughout this chapter is that power should be computed to enforce primarily voltage limits on a cell. The current limits are determined by the electronic design. The constant power limits, the Pmax and Pmin, are determined by other factors in the design. So the SOC limits may be determined just based on how good my estimator is and not wanting to exceed 100% SOC or going lower than 0% SOC or something else. So those limits are in the power limit calculation. I need them, but the biggest assumption we've made here is that voltage shall not exceed Vmax and voltage shall not go lower than Vmin. That's not really the true issue, though. If you talk with a cell designer and you try to get out of that person, what is Vmax? Say, is it, how about 4.2 volts? And they say, yes, 4.2 volts. That's a great voltage to use for this cell. Say, well, is it possible to exceed, say, 4.3 volts? And they say, oh, for a short period of time, 4.3 volts, that's okay, you're fine. So how about 4.4 volts? And they look really nervous because 4.4 volts is really pushing things. And they say, well, maybe for a very short time, 4.4 volts is okay. And if you have this discussion and you think about what is really being conveyed in this discussion, the cell designer is telling you that the terminal voltage is not the issue. It could be 4.2, it could be 4.3, it could be 4.4. The issue really is something that's happening inside the cell, not something that's happening at the outside. There's some internal variable that I need to put a limit on in order to make sure that the cell is safely operated. And it's related to degradation or a safety event. I don't want to cause excessive degradation, and I do that if I maintain the cell at 4.4 volts for a long period of time. It's going to degrade really rapidly. But if I just do a 4.4 volts for a second, it's not so bad. So the compromise that we're making is a compromise of complexity. Voltage is easy to predict. Voltage is easy to measure, but really we probably want to compute our power limits based on internal cell variables. And that's one of the really biggest motivating factors for having cell models that are chemically based rather than empirically based. So our next chapter is going to look at this just a little bit. We don't have much time left in this course to do a really detailed investigation of power limits based on electrochemical models. Hopefully we'll have a future course that looks at that. But at the moment, we want to at least have a glance to look at the ideas. So we need to understand how cells age in order to take advantage of electrochemical models, and we need to look at some more advanced power estimation algorithms that can take advantage of those aging models. And that's what we'll do with our final chapter with the remainder of this course.